Hi everyone, I'm Xinming. I'm happy to present the paper Boundary Rationality in Las Vegas, Probabilistic Finite Automaton Play Multi-Armed Bandits. It's joint work with Professor Joe Halpern from Cornell University. Traditional economics assume people are fully rational and always maximize utility. In reality, however, we see many irrational behaviors. For example, consumers often select a product that's good enough rather than go through all options to find the best one. So we began the study by asking ourselves, is it possible that people are indeed rational, but simply have limited resources, like memory or computational power? We decided to look at a concrete example of slot machines. Imagine you're at a casino. If there are 1,000 slot machines to choose from, what will you do to find the best one in order to maximize your long-term payoff? This is in fact a multi-arm bandit problem. Formally, we can define a k-arm MAB as a tuple. Each mu_i is the distribution over possible rewards of arm I. In the paper, we assume there are two possible rewards, 1 and 0. There are many protocols for the MAB problem. One of them is Thompson sampling, which uses Bayesian methods. Another is epsilon greedy, which explores with probability epsilon and otherwise exploits. They are very popular, but both use infinitely many states and therefore not very human-like. In contrast to previous work on MAB, we wanted to find a more human-like protocol that uses relatively few states and is nearly optimal. We want to show that given resource limitations, human behavior is actually quite rational. We decided to model resource-bounded agents as probabilistic finite automata. A PFA is just like a regular finite state machine with states and inputs, except its action and transition functions are probabilistic. We first came up with an idea of Elimination Tournament, which is to compare arms in pairs until we find the best one. Specifically, we alternately play two arms for about n steps and keep track of the relative successes using a counter. Based on a threshold m, we decide which arm is the winner and eliminate the loser. We repeat until only one arm is left and keep playing that arm from then on. Note that here we stop a comparison with probability 1 over n. We could have used another counter, but that would cause us more states. The protocol uses finite states, but it's not really human-like because people may not alternate between two arms systematically. Also, it can be very costly to switch. Imagine two slot machines quite far from one another. Will a gambler run back and forth to pull the arms? I don't think so. To tackle the problem, we therefore propose the second aspiration level protocol. The high-level idea is to play each real arm against a virtual arm and stop as soon as we find a good enough and hopefully the best arm. So what exactly is the virtual arm? It's just a success probability that we hope some real arm will beat. The probability is represented by ranks. For m possible ranks, rank r corresponds to a probability interval, 1 r minus 1 over m to r over m. So we take its midpoints as the success probability, p equals to r minus 0.5 over m. We start optimistically with rank m, which we called aspiration level. We want to start a level high and we'll gradually lower it. Similarly to the previous protocol, we run a tournament for each real arm I against the virtual arm, and also use a counter to keep track of the relative successes of arm I. However, since we're not playing against a real arm, it's a bit different for updating the counter. We do so probabilistically. Every time we pull arm I, if there is a success, we increase the counter by 1 with probability 1 minus p. This is the probability that there wasn't also a success with the virtual arm. If there's a failure, we decrease the counter by 1 with probability p. As an analog to the previous point, p is the probability that there wasn't also a failure with the virtual arm. We say arm I beats the virtual arm if the counter hits M1, if we keep playing arm I from then on. If the counter hits minus M2, we go on to the next arm I plus 1. Notice that here we have two different thresholds, M1 and M2, which I will talk a bit more in the next slide. If no arm beats the virtual arm in the end, that means our aspiration level is too high. We need to lower it by decreasing the rank R by 1 and restart the tournament. So why do we need two different thresholds? The intuition behind that is if a real arm wins the tournament, we keep playing that arm from then on. However, if the virtual arm wins, we just continue to look for another, hopefully better arm. The cost of mistakenly declaring a wrong arm to be optimal is much higher than the cost of temporarily eliminating an arm that might be optimal. Therefore, we want M1 to be larger than M2. The aspiration level protocol is finite state. It's also quite human-like. Firstly, we start optimistically with a high aspiration level. Secondly, we declare the optimal arm once the real arm wins the tournament. This corresponds to the notion of satisficing, which is to search through alternatives until a threshold is met. Thirdly, we use the smaller M2 to temporarily eliminate arms. That's indeed a negativity bias, which means that people react more quickly to negative outcomes. Finally, we want to evaluate the performance of various protocols. We define the expected regret as the difference between what we could have got and what we'll actually get using the protocol. We say a protocol is optimal if the average regret tends to 0 as n goes to infinity. As shown in a number of papers, Thompson sampling is optimal. However, we prove a theorem in a paper saying that no PFA can be optimal. In particular, its average regret as n tends to infinity will be positive. Even so, we can make our PFAs nearly optimal with epsilon as small as possible. We use simulation to compare the performance of different protocols. As you can see in the figure, our two PFA protocols are nearly optimal. In fact, they outperform epsilon greedy and not too far from Thompson sampling, even though the other two use infinitely many states. To conclude, we propose two finite state protocols, the Elimination Tournament and Aspiration level. They're both nearly optimal, but the latter is more human-like and has no switching cost. Thank you so much for listening.